So welcome to my presentation for my master's thesis in applied mathematics and statistics. And today we will talk about hot processes on social media and mass media. And in particular, we will do a case study of the Black Lives Matter-movement in the summer of 2020, last year, that is. So, and this was done as an next job for Commient Mix also. So just gonna mention that, and big thanks for them for making this possible. And it was supervised by Ras Sandin. So the context for this is that it's a part of a money markets and media intelligence project at Commient Mix. So what has been done is basically the media part where we want to interact with Twitter. And so what exactly is Twitter? Twitter is a social media, and it's a microblog where users share short text messages known as tweets that also might contain media and URLs, links to other homepages. And it's like the unique thing about Twitter is that it's asymmetrical in nature, meaning that users may interact with other users even though they're not following each other. So if you compare this to Facebook, you can only interact with your friends that you know in real life. In Twitter, you can interact with everything from politicians to companies who have Twitter accounts, etc. So it's like an open forum basically, where users can see what they're saying to each other. And you may also tag your tweets using hashtags to spread to get a bigger spread of your content that you're sharing. So let's look at an instructive example of a tweet. So here we have one tweet by Liam Gallagher. And so for users that follow him will see this tweet when they open up their Twitter app or webpage or whatever. And users may also then retweet this. So you see here that user Celestial has retweeted. It's the same content, these two tweets, but it is being shared basically. So the users that follow Celestial will then be able to see this in their timeline. So this is how information is spread basically in Twitter, by sharing other content to a new user bases. And for the mass media part, we looked into the GDELT-project, and GDELT is basically monitoring all news in the world in a real time. And it's quite complex. So to just make things easy, like the fundamental of GDELT is that we have records, and the easiest way to think of these is to think of them as news articles, but they can also be transcribed news broadcasts and other stuff. But the easiest way is just think of this as articles. And on these articles, this text, we use a coding framework that identifies events and actors being recorded. So the records from mass media are being coded, so to say. And let's look at an example of so let's say we have a record, and in this record we have this sentence, that very actual example, that President Reagan has threatened further action against the Soviet Union. So in this coding framework then, they identify the act of threatening as the event, and also identify President Reagan and the Soviet Union as the actors relevant to this event. So GDELT is then basically two data sets. So we have the global knowledge graph, which contains these sources, these records of news, and that is being updated every 15 minutes, parsed. And during this parse procedure, the events are then identified. and they are stored in another database. So they are linked to each other. So we have the original records, and then all the events that are being identified are in another database. And then like for one event, you have all the records that mention that event. So yeah, that's like the very fundamental basic run through of what GDELT is. It's quite complex, and I could probably spend an hour just delving into the details. But that was what we used for the mass media aspect of this project. All right, let's look at how we handle the data. So we had to do some data engineering. So what was done was that a streaming job was set up that monitors a set of relevant companies in the comment network, and also their competitors' accounts. So streaming job basically means that in real time we're capturing all the tweets that are relevant to these companies. And yeah, these tweets are represented as JSON files. And so the pipeline is that these JSON files are stored in so-called Delta lakes in Databricks, which yes, is a fancier database, I guess, but it makes things very fast and easy to work with. So from this, schema inferring was done so you can work with the data, like the transform data in a Spark context, like work in Scala or Python and use SQL and stuff. So here's some streaming statistics. So it's been up for 17 weeks now, and we have almost 200,000 tweets collected during this time period. Yeah.
1.9 million.
Oh, okay, thank you. Yeah, 1.9 million. All right. So how does Twitter look like in a raw data set? So like I said earlier, it's a JSON file, and the easiest way to explain this is that this JSON file contains our two objects mainly. So we have the tweet object and the user object. And for the user object, the relevant part is that we have an unique ID for every user, and also every user we can get the number of followers and the number of friends this user has. And friends meaning the number of accounts that this user follows. So it's not a friend in a sense of like a mutual exchange, whatever, mutual relationship. And then for the tweet object, the most relevant things are that we have a timestamp and also a unique ID for that tweet, and the context of the content of the tweet in the text. And then also in this tweet object, the user object is included for that user of the tweet. So this points back to this user object. So we have the ID and friends, etc. And yeah, I guess for this thesis, we mostly looked at the retweet status. So that is another tweet object. So that will have the original tweet will have its own timestamp, its own unique ID, and also the user of the original tweet. So note that if we look at the user object again, we have no network structure between users. So we do not know, we cannot say anything about how users are following each other. We only have the tweets basically, like we have the timestamps and a lot of information about, this is just the basic. There are a lot of other stuff in this JSON thing, such as medias being shared in URLs and stuff. But the main idea is that we don't have any way to say anything about the social structure of Twitter users, and also that retweet status, it only points to the original tweet. So like one tweet may get retweeted. So user B might retweet user A, and then user C might see user B's retweet and retweet that. But we do not capture that. We only, like from this API, we can only see that user C has retweeted user A. So every every point of retweet will point back to the original tweet. And this will be important then when we're trying to formalize this problem. But let's move on. So we did a case study and focused on the protests taking place after the killing of George Floyd last summer. And why did we choose this? So it's a great example of things happening in the real world that were like they had a cataclysm in the social media, and then things happen in the real world, and when things happen in the real world, mass media reports that. So it's like the perfect example of social media and media interacting basically. So what happened then, I guess most of you know this, but George Floyd was killed by a policeman the 25th of May last year, and this was recorded and went viral the same night on Facebook, and straight away protests starting happening in the US, which then spread across the US and eventually led to the largest protest in US history. And protests also spread internationally. As you might remember that there were protests in Stockholm last summer also. And so what exactly is Black Lives Matter? So Black Lives Matter is a grassroots movement, and it's very connected to social media. It does not have an organization structure. Is decentralized, and all of the mobilization takes place on social media basically. And it's been around for 8 years now, since 2013. And the main issues is that of police brutality against African Americans in the US, and also other issues, policy issues, and related to racial injustices. And from this, a few counter movements, such as All Lives Matter and Blue Lives Matter, has risen up. So, and Blue Lives is for, it's pro-police basically, and All Lives is saying you shouldn't just focus on Black lives, whatever. And so, but yeah, like I said earlier, the nature of this movement, that it's very connected to social media, is why this case study, like that's the motivation why we chose this data set. So we had this data set of collected tweets, for 41.8 million collected tweets from the whole time span of the movement, starting from 2013 to the last of June last year. And so you are not allowed to share full tweets or full JSONs of tweets according to the Twitter terms and agreement. So what we only had was the IDs of these tweets, and so we had to basically set up another infrastructure to get from these unique IDs for every tweet, get the full tweets in JSON. So that meant that a new infrastructure to retroactively get tweets into Databricks was set up using a Python library Torque, which handles some limitations of how many tweets you can request, etc. And had to basically redo a lot of things, but which is good. So now you can get tweets that are retroactively treat them as the same way as we did with the streaming jobs. So let's just look at some data analysis quickly. So this is how on Twitter, how the events unfold. Starting here, this is 25th of May, where George Floyd was killed, and you can see things starting to escalate more and more, and peaking here at around the 8th of June, and then going down a bit but peaking. So something was definitely happening on social media, of course. So, and the nature of these tweets is this. So as you can see, more than 80% of the tweets in this data set in this time period are actually retweets. They are not original content. So most people just share other stuff.
Can I ask a question?
Yeah, of course.
So the tweets collected here, were that tweets that included the hashtag Black Lives Matter?
Yeah. Exactly. So the data set is public, and it collects tweet with the hashtag Black Lives Matters, also Blue Lives Matters, and All Lives Matters. And yeah, there's a whole on how they did the collecting, but yeah, the hashtag was definitely used, and probably used some other things to get related to that. Yeah. All right. So let's look at the mass media aspect of the events unfolding. So these are records or articles mentioning protests in the same time period. So we can see here that yeah, it kind of follows the same pattern. These are the two plots compared log scaled. So yeah, it seems to some sort of relationship. And like the original idea was to basically link URLs in Twitter. So people would share news articles, and we would try to get those news articles in GDELT and somehow like trying to say something about that. But it was quickly found out that people really don't share news that much in this data set. What was shared was actually media as in videos and pictures, basically. So for all tweets with 1,000 or more retweets, we have more than half of them are containing some sort of media, pictures and videos, usually of protests taking place. And compare this to, like, if you look at all the original tweets, then they're only 70% of this. So this is quite significant that like, media seems to play a big part in this, of how tweets, like what was popular in this data set. So next step was to look at how users interacted in a way that the API allowed us to do. So what was done was that we had this directed graph of a retweet graph, actually. So the nodes are users, and every edge here is for the number of times a user has retweeted another user. So let's say for user 0 and user 3, then user 0 has, this says that user 0 has retweeted user 3 3 times, and user 3 has retweeted user 0 1 time. So the arrows are pointing like outwards. And yeah, some basic graph analysis was done. So look, we seen that they were all in the same connected component, and from this one can also get the most popular or most retweeted users by simply looking at the outer greets of every node. And some interesting users were found. So there's one very active pro BLM journalist, who posts a lot of video content from protests, and also one anti BLM journalist. And both of these have very huge followings. So these users will be interesting later and to look at. And what was also interesting that there are a few users that did not have a lot of followers, but were retweeted a lot. So the question from this is basically like, how does this happen? How does a user with 1,000 followers get a tweet retweeted over 100,000 times? Like, how does the diffusion process of this sharing look? And also a label propagation algorithm was run, and yeah, the most interesting communities, or the label propagator for community detection. So there was one big community for the BLM tweets, and by looking at the most retweeted tweets, like of the 20 most retweeted, 18 of these were in the BLM community. And the 20 most retweeted users, 18 of these was in this BLM community, and one of them were in the Blue Lives Matters, and that person was this anti-BLM journalist. And you should know that this community of the Blue Lives Matters was quite small. So
how did you so after running your label propagation algorithm and determining these communities,
yeah,
how did you arrive at these heuristic interpretations?
Oh
of
yeah,
communities?
it was basically looking at the data and.
But it
yeah.
should be like like thousands of users. So did you have some sort
Yeah,
of?
of course. No, it was. It like this algorithm is a heuristic.
Okay.
And, so I mean, I'm not drawing any like final conclusions from these communities, but it seems to be doing a pretty great job. Like in the anti-BLM community, like a lot of famous like right-wing journalists, conservative journalists were politicians, Republican politicians, also like politicians from the former Brexit party. So it seems to be doing an all right job. But yeah, it's just a heuristic. Like you shouldn't.
Cool. Yeah, it might be interesting to sort of verify these heuristic
of course.
determinations using some sort of sentiment analysis or something like that.
Yeah, of course, that would be the next step. But yeah.
Thanks.
No worries. Okay, so by analyzing the data, we have a few questions then. So this diffusion process of information or tweets being reshared, can we model this? So for example, how does it come that a user with a very small following can be retweeted 100,000 times? Can we say something about that? Can we model that? And what role does influential users play in this diffusion process? Like people with a lot of followers, basically. And also, like, how can we look at the interaction between mass media and Twitter? So these are the main questions which we'll start looking at now. So like I said earlier, due to the API of Twitter, we have no social structure. And fundamentally what we have is that GDELT is, we have records and events happening in time, and Twitter is tweets happening in time. So we have points in time, basically. So what can we do with that? So the natural choice would be to implement point processes. So we thought about doing like network analysis, but yeah, due to the restriction of the API, point process was the natural step to take. So let's talk a bit about that now. So we found a point process with a self-exciting, that captures a self-exciting phenomenon known as Hawk processes. What this is that you have a history, a set of timestamps up to time t, and then for that time, then we have this intensity function with a baseline intensity and also a sum of where you sum over these previous timestamps, and then you have this memory kernel that influences how the intensity of former timestamp influences future events. So let's look at this basic example. So here's the baseline intensity, mu, and then here we have the first event happening. Then the intensity spikes, and then it starts to decay a bit, and then another event happens, and it spikes again. And yeah, it's so every time something is happening, the probability of a new event happening increases. So then you get this self-exciting loop, basically. So this has been used to model earthquakes. So we have aftershocks after an earthquake, and it's also been used in finance. And so this is a intensity for Hawk's process in one dimension. And let's look at a multivariate Hawk's process, which we also use. So the same thing here, we have a set of timestamps. This time we have, for D dimensions, we have D sets of timestamps. So we have timestamps happening in different dimensions. We'll make this clear sooner, what these dimensions actually means. And then it's basically the same as before, but instead, so we have this, we do not only have the self-exciting thing here, but also a mutual exciting things between things happening in different dimensions. So let's look at another instructive example here. So here we have two dimensions, And these little things here are events happening, timestamps for events. So first there's an event happening in dimension 1. So then we see a little bit spike here in the intensity, but we also get a spike in the second dimension, even though nothing has happened here. So events happening in one dimension influences events happening in the second dimension. And vice versa. So we see here that nothing is happening in dimension 1, but something is happening in dimension 2, but the intensity increases. So we use this multivariate thing to model, to try to talk about the interrelationship between mass media and social media. So yeah, this kernel thing is, there are a lot of different choices for kernels. So what we used for this one is the exponential kernel. So yeah, the alphas basically means how big this jump is going to be. So the larger alpha, the larger the jump is from dimension j to I. So like how much the mutual excitation influence each other. And this should be a beta, is the decay in that parameter. So how fast this decaying process goes. And yeah, this is an exponential with yeah, this is monotonically decreasing this exponential thing, so that after a time events become irrelevant basically. So it only affects things in the near future. So how did we do this? We had one dimension with the original tweets. So the time span was the first 30 hours of when the protest started happening. So for the multivariate talks, we had one dimensions with the original tweets in the BLM dataset, and also for the second, we had records mentioning protests from the GDELT dataset. And so this is the model then, in 2 dimensions. And this was estimated using a Python library called Tix. And yeah, this should also be a beta. So what Tix does is you give a set value beta basically, and then uses some complex method of least squares to pretty quickly fit the rest of the parameters. So a null hypothesis was then set up, which says that there is no interplay between protests in media and in media and social media. This is, in math language, this is that the alpha parameter is A2, which means how much dimension 2 GDELT affects Twitter. It's the same as how much Twitter influences social media. And yeah, the hypothesis that these should be 0. Then this would mean that there is no relationship between these. And I don't know why the betas disappeared, but this should also be a beta. So simple assumptions were made that all betas are equal. So there's only one beta. So all kernels will decay in the same rate in all dimensions. So different betas were tried, and by simply looking at the highest likelihood, we fixed one beta. And with a fixed beta, bootstrapping by sampling from the set of the GDELT records and tweets was done 100 times. And these were the results. So we get this confidence interval. These are these two are the interesting parameters. So we get these confidence intervals, and we see that this does not contain 0. So with a 95% confidence, we cannot reject the null hypothesis according to the wall test that these parameters are in fact 0, which means that we cannot say that there is no interrelationships between social media and mass media. It is also worth noting that in general, like the alpha 2.1 is bigger than alpha 1.2, and this suggests that mass media actually has a larger impact on what is happening on Twitter than vice versa. Shouldn't draw any like big conclusions from this, but it is interesting to point out. And of course, this is quite a simple model. So like if you can see this as the first step of doing more interesting work, but for like you can make the problem a lot more well-defined by simply looking at different kernels and not trying to like get a proper estimate of the betas and not just fix them, because it seems a bit naive to assume that things are decaying in the same rate in both social media and mass media. Like they're in the same nature. And the next step would be to look at the Granger causality to make a better assumption of predictive causality. And this Granger causality exists for Hawkes processes. So there is work that is done on that. So that's, if someone is interested, it's just to dive in and look at the relevant papers. Let's move on and go back to Twitter. So then we have these two questions, which is modeling diffusion process and look at the role of influential users, basically. So we will look at the retweet cascades, which means that we have one original tweet and then all the retweets of that tweet. So only retweets of one particular tweet. And there were some phenomena that we were interested to capture, first being the word-to-mouth spread, which means that when one user shares something, this will spread out to new users, which will then, they can then share that. So yeah, information spreading like organically in a chain of events. And also the phenomena of like users with more user followers should be more influential. And the phenomena that things are happening very fast in Twitter, that after a few hours, the relevancy of tweets die out, and the content quality. So yeah, good tweets should get, whatever that is, should get retweeted or create more, create like a high probability of being shared than bad tweets, whatever that is. So again, Hawkes process came to the rescue. So the kernel basically, the self-exciting thing captures the mouth-to-spread thing. And by using and also the memory over time that it decays. By using a marked power law kernel, which looks like this, we are also able to capture these phenomena of magnitude of influence and content quality. So let's look a bit more on these parameters. So the kappa is just the quality of the tweets. So the higher kappa, the bigger jump will be done in the Hawkes processes, and the beta determines how much an impact the number of followers. Oh yeah, sorry. So for this, in this marked power kernel, we do not only have timestamps, but also each timestamp has a mark, which the mark is the number of followers that the user who retweeted at the time has. So it's just a constant, and the higher the mark, the higher the intensity will increase at that event. And yeah, this is determined by the beta, and yeah, this is monosolid decreasing. Oh, my pen died. Okay, and yeah, so the final model for a retweet cascade looks like this then, where it has this intensity. But note that there is no baseline intensity for this, since we're assuming that everything that's every retweet is a consequence of another tweet happening in that same retweet cascade. So there are no retweets coming from the outside in this model. And this was fitted by looking at the log likelihood function, and this is nonlinear and optimized numerically in an R package called Evently. And this led to some computational limitations. We had this pretty huge machine with 60 gigs of RAM and 16 cores. And although we could not fit retweet cascades larger than around 3,500, due to this slow numerical optimization, we ran out of memory. This was a bit quite a shame, or like it's 3,300 tweets are still pretty big cascades. But in the data set, we had cascades that were like 200,000 tweets. So which would have been fun to look at, but yeah, computational.
Alfred?
Yeah.
Here, when you say 3,500 tweets was the limitation, does that mean 3,500 instances of retweets of a single?
Yes, exactly.
Tweet? Okay.
The retweet cascade. Sorry if that wasn't clear. So we're only looking at retweet cascades, which is one tweet and all the retweets from that.
Perfect. Thanks.
So this is the same. This is the same. And yeah, let's look at some plots here. So a lot of fittings was done on the two prominent journalists that were found earlier in the data sets were examined, and yeah, both of these people have a pretty huge following. So and all of the plots pretty much look the same. So we have this big spike here in the beginning, and it starts to die down a bit. And I mean, some might go up a bit, and like the only difference were like how fast was this dying down, and so, but otherwise, like the main high level idea is that you have this a lot of intensity at the beginning of things. What was more interesting was looking at retweet cascades where the users did not have a large following. So we can see here that this is a retweet cascade of 1,500 tweets. And it was initiated by a user with only 268 followers. So it's definitely punching above its weight here with the retweets. So then we can see, yeah, this is intensity on the y-axis. So then we see that it starts out pretty slowly, and then something happens here, increases the intensity a lot. And also there's another spike here. So it seems it's like something seems to happen here, and what could that be? So this leads us on to the next and last questions, which is the impact of influential users. So the natural implication is that this is that here someone with a lot of influence has retweeted the tweet, and thus like the tweets get more exposure and then get shared a lot because of the influence of these users that make these big spikes basically. So let's remind ourselves that due to the Twitter API, the actionable branching structure of a retweet cascade was not captured. So what we have is this, it's annoying that my, whatever. So this is what we basically have, this, you can see my mouse pointer, right? So we have the original tweet and then all the retweets of that original tweet. But in what could actually be happening is that we have a original tweet, a retweet, And then from this retweet, we have other retweets of that retweet. So this we do not know, but this is how things actually are. So, but the good thing with the Hawks process is that we can estimate a probability of how this branching structure actually looks. And we do this simply by looking at the kernels. So so let's say, look at tweet number 2 and tweet number 3. So then we have the probability that tweet number 3 is a direct retweet like this of tweet number 1. We look at the kernel for with these timestamps, the marked kernel, which takes into account the number of followers. And then we also looked at we divide this by the kernels for the earlier events to get a probability of like an estimate of how likely it is that this tweet was was direct retweet. And also from this we also get a pairwise influence. So what is the probability that retweet, let's see, so like this chain of events from 1 to 6, what is the probability that 1 is an indirect retweet, or 6 is an indirect retweet of 1? So like there's this chain of events happening, and by looking at this we have this thing. So we have the probability sphere from the direct tweets, and then we estimate the indirect by summing over previous events. And from this, we can get a estimate of influence by basically for every tweet we summon these pairwise influences. So this is good. So this doesn't only take into account the number of followers that a user have, but also when in time a user tweeted. So let's look at an example here.
Sorry, Alfred. This parameter Rij,
yeah,
its definition appears to be recursive. So
yeah. Sorry, you're right. So when it should be 0 when. Yeah, exactly. So yeah, you start at the earliest events, and then yeah, you recursively go through it. And for I is larger than j, I guess this is all 0.
Okay, thanks.
So let's look at a simple implementation of this. So here we have the timestamps. This is sorted by influence then. So this is the original tweet first here, which it gets a lot of influence because of the pairwise thing that and this was the first tweet was a user with 1,400 users, 500 almost, and the second most influential user was a user with almost 150,000 followers, which was tweeted at after almost 10 minutes, but whatever, 600 seconds. And but what's interesting here is that the third user, like the influence is not that, the difference of influence is not that huge. But if you look at the followers here, we have that almost like this user has 10 times more followers than this user. But by the virtue of being arriving earlier, retweeting earlier in this history events, you get a higher estimate of influence. And we can also see this here. So very late here, a user with 50,000 followers retweets the tweet, but this user gets a pretty low influence because it's arriving quite late in the chain of events. It almost gets the same score as someone with half the user follower. With half the followers. because of that user tweeted earlier, basically. So yeah,
Alfred, it's 12:45 now.
Yeah, I'm just gonna wrap up. So this method was implemented, and it's easy to use and should be ready to use in Scala. And yeah, that's it basically. We modeled retweet cascades, and it's worth mentioning this model, this same model can be used for prediction. So by looking at the early stage of a retweet cascade, how can we say, how is this going to pan out in the future? This also uses Hawk's processes, and an easy way to estimate user influence from this model has been implemented. And yeah, we also looked at like an the first steps for looking at predictive causality between social media and mass media. Yeah, that's it basically.
Okay, thank you very much. If there are any questions, please ask Alfred directly. Liwang Zong had a question. Rahul Biswas raised his hand. So
yeah, you just join in. Screen.
okay, let me ask a sort of more important question from a sort of corporate point of view, right?
Yeah, of course.
Okay, you sort of looked at this Black Lives Matter movement and GDELT and mass media and as an example, I guess, but why would this be of interest to, say, a network of corporations?
So, well, first thing, this information diffusion process is apolitical. It doesn't. The content of what is being shared is not relevant to the model. And for like an easy like a finished product, we have the influential thing. So we want to, if one wants to see how things are being shared on social media, we get a measure of the influence of users in this process, which is more rigorous than just like by looking at the number of followers a user has.
So for example, if someone is unhappy about buying a washing machine from Electrolux or whatever,
and that things start to spread out, like people share that stuff. Then by these models, we can like identify which users are initiating this, why this is being shared.
And so maybe the customer service department can be prioritized. There can be a priority queue to mitigate, right? For example, I'm just sort of, I know you know this, but I'm just saying this out loud. So
business like information analytics is like, because things are happening on social media and that affects the real world, apparently, obviously.
No, thanks. Are there any other questions?
Yes, any more questions?
So you mentioned pretty early on that most of the tweets, or at least the retweets, I think, were media-based.
Oh yeah.
So, I was curious, when you ran your analyses, did you account for this? Did you do any analysis where maybe you took out the non-media based and just focused on the media based and compared to see if like somehow you can think of the non-media based as sort of noise in this whole process? Like are the intensities somehow better estimated or something like this when you just focus on the media based tweets?
I did not do that, but that's an interesting question actually. Yeah, the reason, like, no, it was more of an insight with the media thing, but that's a good question to like see how they compare actually.
And did you have any sort of, did you do any sort of, yeah, so I think that could be quite interesting to see sort of.
Oh, sure, for sure.
It doesn't surprise me if I just sort of think intuitively about how social media works. It's
Yeah,
much more
definitely.
impressive and shocking to see a
Yeah,
video
exactly,
of
exactly.
a police officer kneeling on someone's neck than it is to see somebody
Like read a 2,000-word article. Like that's not, doesn't have the same punch as.
Exactly.
Yeah.
So it might be evidence like for just sort of treating those things as noise and focusing on like imagery and things like this.
Yeah.
But the other question that I had was about this sort of like retweet network reconstruction based on partial knowledge of the descendants. So like this, the idea that like a retweet does not like if A retweets B, if B retweets A and C retweets B, then you just get A as C is retweeted A, and reconstructing these networks.
Yeah.
Did you do any sort of like benchmarking? I mean, I know it's hard with thousands of tweets, but like when you learned your graph, based on the process you described, did you do any sort of checks to see if like it's learning something reasonable, or if it's missing any sort of seemingly important pathways?
I did not do that.
I'm not sure how one would do that,
Yeah,
honestly, but in an efficient way. But it could be interesting.
It could be interesting. Yeah.
Yeah.
Yeah. I guess you would. I don't know, like how you do that, like if without like actually looking at the.
Yeah, it's a lot of data to go through.
Exactly.
I don't know of any. I can't think of any off the top of my head efficient way of doing this, but it would be interesting to come up with some sort of validation techniques.
Exactly, because this is like a simple estimation of like how the process could look, by taking into account when tweeters are retweeting. And
yeah, I mean the hidden structure in Hawk's processes is actually the offspring process generator, which is a planar ranked binary tree where the ranks give the time ordering. That's the object that's missing. So of course one can simulate the whole process and then do this, right?
Right. Yeah.
All right.
Was this method that you used for learning the tree based on the retweet information, like the little star that you had? Was this something that was known or standard, or was this y'all's new approach?
With what do you mean, with the influencing, or? Yeah. It was not a new idea. It's been done before.
Okay. Thanks.
Thank you. Any more questions?
Alfred, these influencer things is from the Evently research paper, right? The Evently people.
It's actually another paper, like a library called BirdSpotter, which and that references another paper, which.
Yeah, I mean, if anyone wants to go further, this is all going to be in YouTube anyway, with all the live codes and manuscripts in progress. If anyone wants to go further with these ideas, is that you basically have two communities. So one community of like intensive social media researchers who really understand the parameterization and so on. But and then on the other side, we have this much better library by these French guys. I actually know from before.
Yeah. For sure.
And so they are doing very, very clever optimization by controlling all of the recursions. But unfortunately, the Evently and a whole bunch of other libraries that people are using our packages, they just drop down to some generic nonlinear optimization routine. And that's a killer. You cannot pass the log likelihood function because the recursions blow up, because everything in the past affects the future. So so one important thing would be to actually use the TIX library, and re-implement a lot of these influential models using the TIX library's main routines, I think. Otherwise, we can't even go beyond a few thousand tweets, a few thousand events, right?
Oh, for sure. I mean, it should be noted that 3,000 tweets is still a big cascade, so it's not like useless, this model, but. But yeah, like ideally we would like to look at the like 200,000 tweets, see how they.
Yeah. But the TIX package will handle that, though, I think. But You just have to do a grid search over betas and so on.
I'm not sure. The thing with also with the, I don't think the TIX has the power law kernel, which is
No, I know.
I mean stuff like that. I mean, it's yeah.
No, it's not a plug and chug. You have to improve the numerical routines in TIX itself. It's a non-trivial thing. And without power law, you really cannot count for the dynamics that you see in social media, right? With the heavy tails.
Right.
Anyway, I don't have any other questions. We still have a couple minutes, so if people don't have any questions, we can
have one more question
again.
Yeah, I could ask one more if that's okay.
Go
Russ.
ahead.
Oh yeah, go for it.
Yeah. So when you ran your analysis, I don't know what name you're giving this, where you learn the network of the retweet cascade, starting from just like knowing that's like certain people retweeted node A or something.
Mm-hmm.
So you showed this nice graph at the beginning, your Hawks processes, where like these spikes were probably like intuitively they were somebody very influential. Tweeted this, and the idea was to learn these people.
Mm-hmm.
At least that's my intuition. Is like you can treat this as a influencer discovery mechanism, right?
Exactly, yeah.
Were you able to identify these people with your methods and like trace this back?
Yeah. There were a lot of plots done, so I maybe should have included those. But we could identify the timestamps and by using the.
And they were actually like people that under other metrics were determined to be highly influential or something like this.
Yeah, I mean it has. Yeah, for sure.
Cool. It's cool.
Yeah.
That's it.
All right. Thank you.
Yeah.
All right, it's approaching 1, so last. If someone has a quick question, go ahead. Otherwise, we'll wrap this up.
Okay, one thing I want to quickly point out is that Alfred, can I say roughly 90% of the time for the X job was spent on data engineering?
Yeah, it was a lot of Yeah.
So, I mean, it is something, I guess, from a math department or stats department point of view, it's really important to be able to do the data engineering that's needed for the science, and the mathematics. So in that sense, I think I'm very happy with Alfred's extra opportunities.
Yeah, I've been also happy. Like I learned a lot of things, like practically. And also, like, I learned a lot of things by just like, we had this open-ended problem and we're trying to ask some questions, which was hard because like, it wasn't a well-defined question when we started out. And that like this whole learning process has been very rewarding, both from like a practical point of view and also like how to do science, I guess.
All right, thank you so much. Let's call it a day.
Yeah, thanks everyone for attending.
Thank you.
Thanks, Alfred.
Thank you.